Okay, so we're gonna get started. First, I have a question for you. Why doesn't this following question make sense? What is the binary represent? Or I should say, how can I get the binary representation of x? Yeah.
Which doesn't make sense because it doesn't say what bit x is originally in.
No.
And because the binary representation can actually be anything depending on what your system is.
Not quite.
Okay.
Why didn't this question make sense? Because yes, x is already in binary. Everything in the computer is represented with bits, so everything is already in binary. So asking how can I get the binary representation of my variable doesn't really make sense because it already is in binary. Probably the question that you're asking is how can I display the binary of x, right? Which is a completely different thing. And to display the binary of x, you just go through each bit, and if that bit's a 1, you print out 1, and if it's a 0, you print out 0, right? But you just have to be able to look at each of the individual bits, right? Which we talked about on last Thursday, right? Do you guys remember what operator you used to inspect the bit, or inspect the bits of some variable to see if it's 0 or 1? If not, go review the slides because it's totally there, right? We talked about how to look at each of the individual bits of a variable, right? You can use bitwise and put a 1 in the spot that you're interested in looking at, zeros everywhere else. If the result of the expression is true, it means that bit is 1. If it's not true, that bit has to be a 0. Okay. We'll do one more question to make, or a couple more questions to make sure that you remember stuff from yesterday. What does 0, 1, or I should say 1, 0, 1, 1, 0, 1, what value does this represent? Oh yeah, sure, I can make the font bigger. Any thoughts, any guesses?
45.
So I got 45. Anybody agree with that? Well, I could say it might be 45, but how do we know it's not a pig on Old MacDonald's farm? Or a cat, right? Or the color red, right? You're given just an arbitrary bit pattern, you cannot say what it represents, right? You need more information to be able to say what it represents. Now, let's say we wanted to interpret this bit pattern as an unsigned integer, right? We have 1, 0, 1, 1, 0, 1, right? This is 1. This is our 1 spot, our 2 spot, our 4 spot, our 8 spot, our 16 spot, and our 32 spot. So that's 32 plus 8, which is 40, plus another 4, plus 5. So as an unsigned integer, right, it is indeed 45, right? But what happens if we interpreted this number to be a signed magnitude number? What would its value be? If it was signed magnitude, right, we look at our most significant bit, it's a 1. What does that mean? It's negative. And then the rest of the bits are the magnitude, which is 8 plus 4, 12, plus 1, 13. So this would be negative 13. What about in 2's complement? That's not how I wanted it. right? So we know the number is negative, right? But negative numbers are hard to work with. So what should we do? But positive numbers are easy to work with. So we should negate the number, right? If we negate the number and we know what its positive representation is, and that's easy to figure out, and we know the original number was negative, it can be negative the positive number, and we're done. So how do I negate a number in 2's complement? Flip the bits, right? So that would be 0, 1, 0, 0, 1, 0, and then add. Oh, whoa. Oh. You said you want me to begin with apostrophe if it's not. Oh, come on. So add 1, right, which is 0, 0, 0, 0, 0, 1. So this ends up being 0, 1, 0, 0, 1, 1, right, after we add this bit pattern. Let's put one more blank line there to make it easier to see, right? So this is the pattern flipped. Then we added 1. 0 plus 1 is 1, 1 plus 0 is 1, 0 plus 0 is 0, 0 plus 0 is 0, 1 plus 0 is 1, and 0 plus 0 is 0. So this number is 16, 18, 19. But our original number was negative, so this pattern must represent negative 19. Any questions here? Okay. Your first quiz should be up over the weekend. So again, we were talking about floating point numbers last time, right? Remember our floating point numbers, they are represented using scientific notation, but that scientific notation is in base 2, right? And all of our numbers have to have the form 1 point mantissa times 2 to the exponent minus 127, right? So let's say we wanted to figure out what is the floating point representation of, let's say, negative 19, right? So we want to find the floating point representation of negative 19. So what should our first step be? Step number 1 here. Find the binary of just 19, right? So we know that the binary of 19 is right here, right? This is the binary of 19. Is this guy over here, right? The next step, right, is to multiply by 2 to the 0. So now over here, we're going to have this bit pattern, which is 0, 1, 0, 0, 1, 1, right, times 2 to the 0.
Question.
Mm-hmm.
Isn't this just scientific floating, the assignment?
I mean, there's useful information here, but this is how you do it by hand.
Yeah, but what I'm saying is, like, isn't scientific floating the assignment the way it basically converting decimal numbers to their floating representations?
Well, again, like when you read the number in using scanf %f, you already have it in the floating point representation, right? You already have the binary of the float.
Okay.
Right? You just have to display it in a different way than you would normally display it, just by printing out the value and seeing, oh, when I put in 65.0 and I print it out, I get 65.0. I want you to show me what the binary is for that problem.
Oh, so that's not this.
Not quite.
Okay.
Because right now we're taking some decimal number, or just not just some decimal number, we're taking a number and figuring out what its binary or its floating point representation is going to be. So what's our next step after we multiply by 2 to the 0? I think someone said something, but it was kind of hard to hear. So we said all of our numbers, right, they have to be in the form 1 point something times 2 to the exponent. If we look back here, is this in the form 1 point something? No, so what do we have to do? Put it in that form, right? It has to be 1 point something, right? So put it in normal form, right? So when we get into normal form, it's going to be 1 point, right, 0, 0, 1, 1, right? I took my decimal point that's right here, and I move it to the left by how much? By 4. So now I have to multiply by 2 to the what to keep the value of the number the same? By positive 4, right? Because if you multiply by negative 4, you need to move it even more to the left, right? We want to keep the number the same. So we put it in normal form. If we look back here, we know, oops, right over here, we know that 127 is going to be subtracted from our mantissa. So what should we do? But if we subtract 127, and then when we compute the value again, we're going to subtract an additional 127, that would subtract out 256, right? But what I want to end up with is after I do this subtraction, right, my number needs to be to the 4. Add 127 to compensate from the fact that later on you're going to subtract 127. So for the exponent, we need to add 127. So this is equal to 4 plus 127, which is 131. Now we can write out our floating point number in its representation, but in the 3 fields. There's 3 fields, remember? There's the sign field, there's the exponent field, and then there's the mantissa field. How big is the sign field? It's 1 bit big, and since our number was negative 19, what should we put here? 1, right? Our exponent field is how big? How many bits? It's 8 bits, right? So I'm going to be lazy, but, and just write 131 in decimal, right? But you'd actually have 131 in binary. Or if I don't want to be so lazy, I would say the bin of 131, and there we go. That should be 1, 2, 3, 4, 5, 6, 7, 8. So over here, right, the binary of 131. And then we have our mantissas. So what should our mantissa be? It should be 0, 0, 1, 1, right? We don't need to store the 1 point because it's always going to be 1 point something. So this would be 0, 0, 1, 1. And then how big is the mantissa field? So the entire float is how big in terms of bits? Not 16. The entire float is 32 bits, right? You've used 1 bit for the sign and 8 bits for the exponent. So how many bits do you have left over for the mantissa? 23, right? So this whole field needs to be 23 bits big, right? And I've used 4 bits so far, so how many more bits do I need? 19, right? I'm going to have 19 zeros. Should I put those 19 zeros, at the front? Should I put them at the front, or should I put them at the end? At the end, right? Because these values come after the decimal point, and so you want the zeros to be at the end. 1.x 0, 0, 0, 0, 0 is still 1.x. But if you did 1.0000x, that's not equivalent to 1.x anymore. So then we'd have and 19 zeros. So I'm not going to write that. Yes? That's just so it'll actually let me write the 0. The quotation mark is just there because Excel keeps getting rid of the zeros if I don't do that. Any questions here? Yeah.
Yeah, what is the point of that? I think I might have forgotten. What is that 127?
Oh, the bias?
Yeah.
So the 127 is the bias. So the number in the exponent field, it's interpreted as an unsigned integer, right? But we still want to be able to represent negative powers, right? We want to be able to do like 1.2 to the negative 3. So what they decided to do is, since it's an unsigned field, if you subtract, it can have values up to 256 because 8 bits. If you subtract 127, it kind of splits it in half. So if you wanted like a negative value, you'd put something like 125, and you do 125 minus 127, and you get negative 2 for the exponent. I know, it's weird, but that's what they went with. Any other questions? Is it clear on how to convert a decimal value to a floating point value? Do you guys know how to go back the other direction? So let's say instead I gave you this, right? You have this big old binary thing right here, right? Remember, the value of the floating point number, it's 1 point mantissa times 2 to the exponent, right? And then the sign bit. So we look here, right, and we see our number is negative. So we know that we're going to have negative, right? And it's going to be negative 1 point something, right? 1 point the mantissa. The mantissa is 0, 0, 1, 1, right? Then that's going to be multiplied by 2 to our exponent, which again, this value right here is 131 minus 127. And 131 minus 127 is 4, right? Because we're just going back, right? So this ends up being just 4 here. And after you do that multiplication, right, the decimal point would move to be over here. So you'd end up, you know, that's the same thing as negative 1, 0, 0, 1, 1. And again, if we interpret this bit pattern right here, that's the binary of 19, and we know that it's negative. So it must be negative 19. So that's how you go back the other direction. Given this representation of floating point numbers, what number might be hard to represent? I think I heard it. 0, right? Because can you write 0 in the form 1 point something? No, so 0 has a very special representation. If the exponent field is 0, like literally the exponent field is just all 0 for its bits, it means the number is 0. Right?
How do you represent 1 then?
So how do you represent 1?
As in like regular numbers, that would just be 1.
All zeros would not be.
No, but isn't something to the power of 0, 1?
But again, it's a special representation, and like one thing that's going to be helpful is if you look at this website. So let's say we wanted to see what 0 looks like. So you can see 0 here, right? It's literally all zeros. The bits are all zeros. Let's say we want to represent 1, right? Well, you can represent 1 as 1 point something, right? So when you represent it, it's the mantissa is 0, right? But our exponent is 127. So, right, you have 1.0, right, times 2 to the 127 minus 127, which is 0. So you have 1 times 2 to the 0, which is 1.
Thank you.
So its bit patterns won't be all zeros. One thing that's also interesting is if we go over here in 0, if you have it where the decimal field, let's see, because this shouldn't be, that's just negative 0. So there are 2 representations of 0. I generally believe that if you get like inf or not a number, that's when the exponent field is 0, but the mantissa is non-zero. Which I think I had that, oops, somewhere else. So special values. If the exponent field is 0, then it means that number is 0. If the exponent field is all ones, that's what I was looking for. If the mantissa field is 0, then it means that number is infinity. But if the mantissa field is non-zero, it means the number is not a number. So if we go back over here to our calculator and we change our exponent field to be all ones, it's infinity, right? It's infinite. And if I do here, it's negative infinity, right? But if the mantissa field has a non-zero bits, right, that's a 1 and part of the mantissa, it's not a number. So again, that's some special representation for floating point numbers. So basically everybody follows the rule except 0, infinity, and not number. Right? They follow that same basic format. Any questions? So what about representing characters? How would you do that? I mean, with characters, there's really like no right way of going to do it, right? You just say this bit pattern represents this character and we're done with it, right? There might be certain things that you can do to make your life a little bit easier, but it's really just assigning some arbitrary pattern to mean this representation. Common ones are ASCII values and Unicode. ASCII uses only a single byte to represent all the characters on your keyboard. 1 byte ends up being fine for English because we have a very small character set. But other languages like Chinese and Japanese, they have a very large character set. And with only 1 byte, 8 bits, you can only represent 256 characters. But there are more than 256 characters in Chinese and Japanese. So you just got to use more bits, right? So they use Unicode, which is 2 bytes big, so 16 bits. So they have 2 to the 16 possible representations that you could do, which is 65,536 unique characters within that character set, which is more than enough to be able to cover these other languages. One thing to point out, though, is let's say we do look at the ASCII table, is again, they're just bits for our representations. But if you notice in the ASCII table, all of our uppercase letters are next to each other. All of our lowercase numbers are next to each other. And they have corresponding like binary patterns that are just like one more than the one that comes after it, right? So A, right, it could be considered to have decimal value 97. But B has decimal value 98. C has decimal value 99. So if we're over here in Python, if I ask for the ord of A, which just says give me its numeric representation in bits, right? Because Python won't let me compare the characters directly together, right? If we compare this to 97, it's going to return true, right? Because they happen to have the exact same bit pattern, right? The bit pattern for character A and the bit pattern for 97, they're identical. You can't tell the difference between the two, right? And it's only the context that allows us to figure out which meaning we want to use. But this also allows us to do certain things where we could try to treat our characters like numbers. So if A, little a, it has the value 97, if you do 97 plus 2, you're going to get 99, right? Which also happens to have the same character representation as C, right? So here we could do something like, is the ord of A, right, plus 2, is that equal to the binary representation of the ord of C? Yeah, sure, it is. Or you could do chur, which says take this numeric value and give me back the corresponding character. Right? We could do something like the ord of A, which again just 97, plus 2, and that's going to give us C. Now, in C and C++, you don't have to do this whole ord chur thing. The C compiler is fine treating the characters as numbers. So in C, you can just do something like C plus A, or C plus 2, and you're going to get 2 letters after C. Or A plus 1, or A plus 2, and you'll get 2 letters after A. What do you think you would get if you did something like this? C minus A. Again, assuming you're working in C. 2, right? Because if you look back at the chart, C has 99, A has 97, 99 minus 97 is 2. right? Might also be why, you kind of get like this weird behavior when you compare strings. Like, is zebra, is that less than apple? What do you think? Is zebra less than apple? True? False?
Oh,
Uh-huh.
is it gonna do it alphabetically?
It'll compare the characters, right? Individually, right? Zebra is less than apple. You might be like, why? That makes no sense. Well, if we look over here, it compares each character one by one. What's the numeric value for Z? 90. What's the numeric value for A? 97. Is 90 less than 97? Yeah, so big Z comes before little a, which is, kind of explains why you do have that kind of weird case-sensitive behavior when you're comparing strings. Does this make sense? Right? And you can utilize like this addition and this arithmetic with characters to make a lot of your current homework assignment much easier than if you don't exploit this. Any questions before we continue on? Wrong thing. So arrays are, like we talked about, basically Python lists. But in C, there's two different ways to kind of make arrays. There's the static way and there's the dynamic array. But when you request an array, whether it be dynamic or static, all of the elements will be next to each other in memory. So if I do AR10, it's going to make space for 10 integers. That first integer in that array, maybe it's at location 100. That means the second integer in the array has to be at location 101. And the third one has to be at 102, and the fourth one at 104, and so on. They have to be next to each other in memory, otherwise things aren't going to work correctly. They won't be randomly scattered. So AR itself is actually going to be a pointer to the beginning of this space, right? So when we're doing something like AR at I, square brackets, it's really just shorthand notation for AR plus I dereferenced. And we come back here. I don't know, maybe make a new sheet. And we make everything big. Right? So when I do something like AR at 5, right, this is going to make a new array of integers. Once I type an int there. Yeah. Oh, I thought I did. I swear I changed it to 14. Maybe I have to click on all the fields and say change them all to 14. So again, here we might have our addresses, right, in memory. So we might have, again, like 100, 101, 102, 102, 103, right? We can just keep going. Right, memory goes on. And it may happen that this array begins at address 100, right? So over here, we might have, array at 0, array at 1, array at 2, array at 3, and then array at 4. What value does array have? Yeah, the value of AR is 100. It's just a pointer to this beginning location in memory. So when I do something like AR at 2, right, this is equivalent to star AR plus 2. So what's AR's value? It's 100. 100 plus 2 is? It's 102. So go to location 102 and get the value that's there. So go to location 102 and we get the value that's there, which would be the value of array at 2. Does that make sense? Right? And this little math of like doing the AR plus I would not work unless the elements were next to each other in memory. So single-dimensional arrays are fun and all, but let's get to the good stuff, which are multi-dimensional arrays. When we have multi-dimensional arrays, there are two different options that we can utilize. One is one big chunk. So when we allocate our array of, say, 3 by 4, instead of what we could do is just make space for 12 elements. Or if we make space for a 5 by 4, make space for 20 elements. Or if we make space for something like a 2 by 3 by 5, well, that's 2 times 3 times 2 times 3 times 5, which is 6 times 5, or 30 elements, right? You just make space for one single dimensional array, one fat chunk, and then we just have to do some math to be able to locate the elements. This is what happens in C when you statically create arrays. So when you do something like int AR34, it's actually allocating one single fat chunk of memory for it, right? The other possibility is an array of arrays, which you'll see in a moment. What we do is we create an array of pointers, and then each of those pointers point to a row of our two-dimensional array. This is what's done like in Python. This is what's done in Java. This is what's done in C and C++ when you dynamically allocate the space. So with one big chunk, we have a couple of options. The first thing that we might decide to do is, how should we lay it out? Should we lay out our rows end to end, row major, or should we lay out our columns end to end, column major? Row major is used by C, and column major is used by R. So over here, if this was our row major matrix, which is a 3 by 4, right, it has values 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And so when we're going to put them into memory, we're going to do the first row, then the second row, then the third row. So notice we have 0, 1, 2, 3, right, our first row. And what do we have in our array? 0, 1, 2, 3, followed by the second row, 4, 5, 6, 7, followed by the third row, 8, 9, 10, 11. So you just stack them each row next to each other, right, in that one big chunk of memory that you made. With column major, we're going to lay our columns end to end. So we'll have this column, then this column, then this column, then this column. And if you look at how the memory is laid out, it's 048, 048, 159, 159, 2610, 2610, and 3, 7, and 11. Any questions on row major or column major so far in our one big chunk scheme? Okay. So now, right, we have to figure out how we're supposed to do our mapping, right? If we're over here in our one big chunk, right, we still want to be able to do array at ij to be able to access the element, to be able to figure out where it's at, right? So if we pop back over here to row major, right, if I do my array at 1, 2, I want to be able to pick out element 6, this guy right here. So we want to think about this. How can we come up with some equation that's going to represent the behavior that we want, right? So again, we have two indices, and maybe this will allow us to copy it easily into Excel, hopefully. Woo, I did. Or maybe I should start that over here. Right, we want to be able to access our array at ij. Or as a concrete example for right now, let's try to access our array at 1, 2. Right, we know that when we access our array at 1, 2, we should get 6. But how can we figure that out? If we think about what's going on, every time we increment I, what does that cause us? So I is our row or is it our column index? It's the row index, right? So every time the row index increments by 1, we have to move to the next row, right? And we've laid out our rows end to end. So every time in this example, our row index increases by 1, how many elements do we have to move past? Well, number of columns, right? In this case, 4, right? Because if I want to move from row 0 to row 1, right, I have to go past 4 elements because these 4 elements are next to each other in memory. If I want to go from row 1 to row 2, I have to go past these 4 elements. And if it kept going on and the column size was fixed at 4, I'd have to keep saying I need to move, 4 elements at a time every time my row index goes up by 1, right? But if we look at the elements within the row, right, they're next to each other in memory, right? So every time our column index increases by 1, if I want to go from 1, 0 to 1, 1, how much do I need to move in my one-dimensional array? If I want to go from 1, 0 to 1, 1, how many elements do I need to move in my one-dimensional array that I'm actually using to store the values? One element, right? If I want to go from 1, 0 or from 1, 1 to 1, 2, I need to move from 1, 1 to 1, 2, one element. If I want to move from 1, 2 to 1, 3, one element, right? So in this example, right, what equation can we use to convert our two-dimensional index, which is what we want to use as programmers, into the equivalent single-dimensional index? Right? What's our single-dimensional index going to be equal to? I times 4 plus j, right? But we want to start at which element? Well, we want to start at the beginning of our array, right? And our array starts at, it's AR. And I don't know why this won't ever let me go back. AR plus I times 4, right? Plus j will actually move us to the right element. And then if we were dereferencing, is it literally impossible to write in front of this? Is this like an insert mode? No. Right? So this would be equivalent to doing AR I times 4 plus j and then dereferencing it. Right? Or if we were looking for some single dimensional index that was equivalent, right, k, our single dimensional index is equal to I times 4 plus j. As Rez mentioned earlier, if we want to generalize and our matrix is an m by n matrix, it's going to be I times n plus j. Does that make sense? Any questions here? Okay. What about if we were doing column major? Right? If we were doing column major and we wanted to figure out our single dimensional index. Notice that when our row increases by 1, right, are the elements in our single dimensional array, how far apart are they when we move up by 1 row? If I go from row 0 to row 1, how far apart are these guys? 1. Or from 4 to 8? 1. Or from 1 to 5? 1. They're 1 apart. But when I move across columns, how many elements do I need to move? 3 elements. Or from here to here? 3 elements. Or from here to here? Oops. Also 3 elements. Right? So again, if we're using the same indices, I and j, and our matrix is again m by n, what's our equation going to end up being? If we were in column major? J times m plus I. Right? Which these are on the next page. Any questions about either one of these equations? Now, in your computer, are you limited to only creating two-dimensional arrays? No, right? You can create n-dimensional arrays statically. So we need to be able to generalize how can we go from, in the one big chunk method, where we have some number of dimensions. And let's see a little bit of an example of this first, so we can kind of get an idea of what we want to have happen. So over here, let's say that we probably need a lot more space to make this happen. You guys can put down there. Let's say that right now our new array, our AR3, it's a 2 by 3 by 4. Right? So if you have a 2 by 3 by 4, the way that you can kind of imagine this is the array when I is equal to 1, and this is the array when I is equal to 2. And now our numbers here, if we want to keep doing new values, would be something like 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, and 23. And so if we keep this going out, got to go all the way up to 23, almost there. But he's a bit big. 22, and one more, 23. So this is what our 2 by 3 by 4 array would look like if it was laid out in memory. It'd be laid out as this really, really long array of 24 elements. But it ends up being the first matrix and then the second matrix after it. Right? So let's say we were trying to come up with some formula to describe how we should access our single dimensional elements, right? Now we're trying to access, right, array at say maybe 1, 2, I don't know, 2. We want to access our array there. Now, every time this first index increases, how many elements do we need to move? We need to move 12 elements, right? The size of this matrix, right? Now, once we're in this matrix, again, the rows are going to be how many elements apart?
1.
The rows will be 4 elements apart, right? Because each row is laid end to end, right? It'll be this row, then this row, then this row, right? So if I want to move from one row to the next row, they are 4 elements apart when laid out in memory. And each of the elements within a single row is how far apart? It's 1 element, right? So let's say we wanted to access our array over here at I, J. So in this case, right, what would our math be to get the corresponding single dimensional array index, given our concrete numbers over here?
AR.
It's going to be, yeah. Well, let's just do the index, just because it always is going to be AR plus your single dimensional index dereference to get there.
1 times 2.
1 times, not 2, right? Because we said when we moved across one row, we needed to move how many elements? 12. How can we get 12 from these numbers?
Times 3.
3 times 4, right? Because that's how big each of these matrices is. 3 times 4. Oops, yeah, 3 times 4. Plus, right, every time this index goes up by 1, right, we needed to move 1 row. How many elements are there per row? 4, right? So it's going to be plus 2 times 4, right? This 2 times that 4. Now we need to move, we're within the row, so how far apart are the elements? They're just 1 apart a piece, so just plus 2 more. So this ends up being, right, 12 plus 8, 20, plus 2, 22, right? And if we look, our array at 2, or at 1, 2, 2, it's 22. And if we go look at address 22, we have 22 there, so we're getting the right number. What would our generalized formula be if our matrix is an A by B by C matrix, right? So I've declared it as AR, A by B by C. And again, we want to access our array now at I, J, K. Why? It's so stupid that it does this. Int AR A B See? So this is going to be, what's the corresponding single dimensional index? I times C plus J times C plus K. Or if you look at it, right, we've taken each index that we have, I, and we multiplied it by the dimensions that came after it, right? We took I and we multiplied it by B and C. We took J, we multiplied it by just C. We took K, oh, there are no more dimensions that come after it, so we don't multiply it by anything. So when you generalize and you want to go row major to n dimensions, the easy way to think about it is it's each index times the size of all the dimensions that come after it. Right? Each index times the size of all the dimensions that come after it. Or if we're really looking for the equivalence of this guy right here, it's going to be, you know, like you guys said earlier, star AR plus I times B times C plus J times C plus K. It'll give you the corresponding element within that array. Right. If you notice how this definition is kind of defined, you can do some really stupid things, right? What happens if this array at the top, we tried to index it at index 0, say 3, 4? What element would we access? So first, if you look at this, does this look like the indices are in bounds? Right? Remember, our array is a 2 by 3 by 4. So 0, that's in bounds. Is index 3 in bounds? No. It's 4 in bounds. No, right? Because you have to be one less, so it should be 2 and 3. But what element will you end up getting here if you did this? Right? Because we're going to do I times B times C, which is 0 times 12, plus J. J is 3 times 4 plus 4, right? So we're going to go to element position 16 in the array. So 16 in the array, it's 16. And if we pop back up here, 16 is actually equivalent to doing array at 1, 0, 0. They're the same thing, because they end up at that same location in memory. Does that make sense? Because you get 16 here, and element 16 is at position, this should be I equals not 1, but I equals 0 here, and I equals 1 here. Right? Element 16 is at position 1, oops, not 0, 0, 1, 1, 0. Right? Gets you to the same spot. And the computer will be happy with this, and it will do it, and it will not complain. So again, like we were talking about, our mappings for n-dimensional arrays, if you're a row major, it's each index times the size of all the dimensions that come after it, and then you sum that up. So if our matrix, our array was D1 by D2 by D3 all the way up to Dn, and then we had these indices I1 to In, then the equivalent single dimensional pointer is going to be, well, index 1 times all the dimensions that come after it, D2, D3, D4, all the way up to Dn. Then we're going to have index 2 plus all the dimensions that come after it, D3, D4, D5, right? Plus index 3 times all the dimensions that come after it, 4, 5, 6, all the way up to n. And then you'd keep doing this until you finally got to the very last index, and that's just going to be that index plus that index, and it won't be multiplied by anything, because there are no dimensions that come after it. With column major, it's the reverse. It's each index times the size of all the dimensions that come before it. Right? So again, if here were our indices that we had before, right? It's index n times dn minus 1, dn minus 2, dn minus 3. All the indices that came before it, all the way up to d1. Index n minus 1 will be multiplied by dimensions n minus 2, n minus 3, n minus 4, right? All the way up to dimension 1. And so on down the line, you compute that summation to get the corresponding single dimensional address. Any questions on these equations? So if you remember all the way back to week 1, when we were talking about C and arrays, right? We said that when you declared a static array and you wanted to pass it to a function, you had to specify the size of all the dimensions but which one? But the first one. Why don't you have to specify the first dimension? But you have to specify the rest. Again, C is row major, but you have to specify the size of all the dimensions except for the first one. Why not the first one when you're trying to pass a static array to a function? When you look at our equation here, is there any term that's missing? D1, which is the size of the first dimension, right? You don't need the size of the first dimension to compute your corresponding single dimensional index. So C's like, you don't gotta pass it. But C does need to know the size of every other dimension to be able to compute this equation. Right? And so that's why with the static arrays, you have to specify every dimension but the first. Any questions about that? Okay, we'll move on to arrays of arrays. So when we have an array of arrays, it looks like this structure over here on the right-hand side. Right? We have our first array, right? It's an array, but what is it an array of? It's an array of pointers. And each of these pointers points to an array of values. So you have an array of arrays. Or in Python, when you have a list of lists, or a vector of vectors, or whatever of whatever, right? You're using this type of structure. So if this is the two-dimensional array that we're trying to implement, right, that we want to represent in the computer, right, we'd have to make 3 arrays of pointers, and each of those pointers would then point to one row of the elements. If you wanted to, you could also do it the other array around, where you created like a number of column pointer arrays and they point, but most people don't like that notation because now the first dimension you'd specify would no longer be the row, it'd be the column. So you'd have to write it backwards. But you could do it that way if you really felt like it. Or if you were clever and you wanted to do it with column major, or like, based on column arrays for whatever reason, you make your own class and you hide it, right, behind some function when they access it. And you do the conversions behind the scenes so they don't have to see it. So let's say we want to access our array of arrays with no brackets, right? When we do array at ij, right, it looks just like a one big chunk access. But it's not. It's actually different, right? Because if we applied this same logic back here, would it work? Right? If I tried to access my array at 1, 2, under the old scheme, right, I would take 1 and multiply it by 4 to get 4, and then add 2 to get 6, right? So I get a location 6 past AR. But if I go 6 past AR, am I going to get anything I want? No, right? So even though this notation is the same as one big chunk, what's going on behind the scenes is completely different how the compiler interprets that code and what assembly code it writes behind the scenes for you. When we do this, right, when I want to access my array at 1, 2, well, first I have to find this row pointer, right, which is, one element past the beginning. Then I have to go follow this pointer to this array and then go to location 2 into it, 0, 1, 2, to get the element at 1, 2. So it requires two separate dereferences. So when you're accessing this array, it's going to be AR plus I, dereferenced, plus J. Dereference that again, right? Whereas if it was one big chunk, we would have had this. So all we have to do with array of arrays is chase down the pointers. So if you look at this expression, what doesn't appear? The dimensions, right? The dimensions do not appear in this expression at all, which is why when you have dynamically allocated arrays and you're passing them as pointers to pointers, you don't have to specify, at least in terms of the type, what the dimensions are, because the compiler doesn't need it to look up the element. So again, if we want to do a little bit more of a concrete example, so over here, let's say I first allocate my array of pointers. So here we have my pointers, and then let's say that this array of pointers, this is where AR is at. AR is going to actually be down here, and he's going to need to point to the first element here. Let's say this first set of elements ends up at location 100, so it needs to be 101, 102, right? We have our pointers over here, and then we have our little arrays over here. So they have like the values, let's say A, B, C, D in the first one, and let's say this array begins at location 200, 201, 202, 203. Then we have our second array down here. Maybe he begins at 450 in memory, so 450, 451, 452, 453. And he might have E, F, G, H. And then we finally have our last array. It's down here. Maybe it's at location 50. So he's at 50, 51, 52, 53. I, J, K, L. So over here, what pointer would we have to store in our array of pointers? Where should this first element point to? So maybe we insert a column over here. Right? These are the addresses. Index. Right? This would be like index 0, index 1, and index 2. So what value would I have to store in here to be able to access the first row of my array? 200, right? To store the pointer to the first element. What would I need to store as my second row pointer? Right? I want to be able to access this second row down here. I would need to store 450. And to be able to access my third row, I would need to store just 50. Now, AR itself, what value does AR have to store in it? 100. So now let's say I do decide that I want to do something like AR at 1, 2, right? The first thing when you're doing something like this is to rewrite the expression as to actually what's supposed to go on. So it's going to be star, right? And then we'll have another star, AR plus 1 plus 2. So what's AR plus 1? What's AR's value should start with?
100.
AR's value is 100. So this just becomes, 100 plus, oh my goodness, plus 1, right? Which is 101. So now we have 101 here, and then this dereference operator says to do what? Go to location 101 and get the value that's there. What's the value that's there? 450. So this becomes star 450 plus 2. So now what's 450 plus 2? 452. And then the dereference says to do what? Get the value that's there, so that it ends up just becoming G. And that's how we chase down the pointers to end up getting the value that we wanted. Right? We went to AR at 1. We went to element 1 in that position, right, to get the 450. And then again, these are like the indices up here, 0, 1, 2, and 3 for each of the arrays. 0, 1, 2, 3. 0, 1, 2, 3. Right? And this is what gets us the element that's at location 1, 2. It is the G. Does that make sense? Right? But there was no mention of the dimensions at all, which is one of the advantages of using arrays of arrays. Any questions here? Okay, so we have these two methods. We have an array of arrays, and we have our one big chunk. What do you think the trade-offs are for using each one? What advantages does an array of arrays have? What advantages does a one big chunk array have? And what might be the disadvantages of them? So give me an advantage of an array of arrays versus, or give me an advantage an array of arrays has, or give me an advantage that an array of arrays has, or give me an advantage that a one big chunk array has.
Well, I think a one big chunk array would probably take up less space.
A one big chunk array will take up less space. Why?
Because an array of arrays takes up a square, no matter how many guys in it don't exist.
Oh, so you're saying that one big chunk is going to take up more space because...
Sorry, less space, I think.
One big chunk will take up less space because...
Because it doesn't necessarily take up the dimensions times each other.
You are right that a one big chunk array will take up less space, but I think for the wrong reasons.
Really.
The one big chunk arrays, they do take up less space, but why? I don't think it's for the reason you're stating, though.
Okay.
Why would your one big chunk array take up less space?
It's clearly defined as limits.
No, not because it has some limitations about how big it can be. Yeah.
Because AR is like a pointer to an array of pointers, but for one big chunk of array, like it doesn't have an extra pointers.
Yeah, right. Exactly. So with an array of arrays, notice we have to have this array of pointers, right? But with one big chunk, did we have to have that array of pointers? No. So there is some space overhead for doing an array of arrays method. And as you go out and you have more dimensions, the overhead's going to increase a little bit as well, right? Because you'll have like an array of arrays of arrays of arrays of arrays of values, right? Which ends up meaning you might have quite a few more arrays. For example, in this example, right, our array was a 3 by 4, right? So how many extra pointers did I have to have? We had 3 extra pointers. What happens if we had a 3 by 4 by 5 array? How many extra pointers do we have to have? So we have 12. So if we think about the first math, are we able to get rid of this first array of 3 things? No, right? So we have an array of 3 pointers, right, from this dimension, right? So we have at least 3 from the first dimension, right? But then each one of those arrays points to another array of 4 pointers, right? And how many arrays of 4 pointers do we have? 3 of them, right? So we get another 3 times 4, right? So 12 plus 3, we're actually going to have 15 pointers for that dimension. or for doing an array of arrays of arrays. It's a 3 by 4 by 5, right? And as you go in more and more dimensions, it keeps kind of having to have a little multiplicative property in terms of how many pointers you want to have. So it does waste some space. So that's one of the advantages one big chunk array has. Any other advantages one might have over the other?
We need 1 pointer for 1 big chunk.
Yeah, with one big chunk array, right, we only need about 1 pointer, which is very nice, right? So there's a constant amount of fixed overhead for a one big chunk array, right? But with an array of arrays, it grows like polynomial in terms of like the number of dimensions. Anything else besides space? So in terms, yeah.
For an array of arrays, you don't need to say what size it is of one big chunk.
Yeah, exactly, right? With an array of arrays, when you're writing a function, right, you do not need to specify as part of the type what the dimensions have to be, right? So that means if I write a or if I write a like matrix add function, right, that accepts an array of arrays, I only have to write one, right? Because the code's going to be the same. But if I want to write or a matrix addition, but I want to do it statically, I have to do it for every different size of array that I want, right? Which is kind of poopy, because the code you'd write would be 100% identical, except one of them would have, okay, this one has 2 elements per column. This one has 3 elements per column. This one has 4 elements per column. This one has 5 elements per column. This one has 6 elements per column, right? And you have to keep specifying for each different possible number of or for each possible size of the number of elements per row that you can have, that value, which could be, very tedious and probably not very beneficial. One of the other advantages of an array of arrays is you don't need to know the size at compile time, right? But one big chunk you do, because with one big chunk you declare it as array 5, 6, or array 7, 8, or array 1, 2, 25, 33, 64, right? You have to know the dimensions at the beginning, right? Or at the very least the maximum dimensions. The problem though is even if you like over allocate space statically using a static array, you will be wasting space when the program's running because the user might not take advantage of all that space, right? But if the user needs more space than that, well, now you're hosed. You can't do it, right? But with the dynamically allocated arrays, the array of arrays, you can make exactly as much space as you need and no more. So that's one advantage of an array of arrays. Array of arrays can also be ragged, which means the number of elements per row don't have to be the same, right? I can have one row could have 5 elements, the next row could have 10 elements, the next row after that could have 3 elements, the next row after that could have 20, right? Because the dimensions don't show up in the equation, right? So it can have different number of elements per row. But with a one big chunk array, right, if you had a different number of elements per row, your math all of a sudden breaks, and so that's not allowed. So there always have to be the same number of elements per row in an array of arrays. An advantage, or in a one big chunk array. Another advantage of a one big chunk array is that lookups tend to be faster because you just have to do some math and then you get the value. Whereas when you're doing an array of arrays, you have to go to this pointer, then to this pointer, then to this pointer, then to this pointer, and finally end up at the location that you want to be at, right? It also does have like some cache performance penalties because the elements aren't next to each other in memory, so they probably weren't preloaded the first time you access them. Whereas with one big chunk, everybody's next to each other in memory, so you do get better cache performance because of that. I think that's everything that I remember, at least. Yeah, that's all of them. So now let's talk about, so I should say now, you know enough to do all the homework assignments. We've covered sufficient information. So if you haven't started on them, totally be doing that. So structs are essentially classes in C. And the way that they actually work in terms of how they're represented in memory is when you declare some struct, the elements in the struct are just laid out next to each other in memory. So if we declare our array where we have declare our struct where we have x, which is an integer, y, which is a character, a short, which is s is a short. We have an array of characters. We have a double and a float. Those elements will just be laid out one right after the other in memory. And when you declare your struct, what you're going to end up with is just a pointer to the beginning of the struct. So it's like an array where the elements are of mixed sizes, but that's fine because we know exactly how many elements are going to appear in this array and exactly what spots that particular type will appear at. So over here, how many bytes big is a integer? Assuming a 32-bit machine. It's 4 bytes big, right? So here we have x. It's 0 bytes past the beginning of the array. It starts right at the beginning. But since x takes up the first 4 bytes, the next element has to appear how far past the beginning? Given that x is 4 bytes big, our next element has to appear how many bytes past the beginning of the struct? 4, right? Because x is taking up the first 4. And so if we look at y, it starts at 4. How big is a character? 1 byte big, right? So so the next value after y, s, it's going to have to appear 1 byte after y, right? But if y appears 4 bytes past the beginning, that means s has to appear 5 bytes past the beginning, right? We have to go past x and y, 4 plus 1, 5 bytes in total. A short is 2 bytes big, so our next element name has to appear 4 for x, plus 1 for y, plus 2 for s, 7. So name appears 7 elements past the beginning. Our array over here, how many bytes big is it? Name. It's 10 bytes big, right? Because we have 10 characters, and each character is 1 byte big. So 10 bytes past name, we're going to have our next element, which is d. So he's going to appear at 17. Our double is 8 bytes big, so 8 bytes past d, we'll have f. So he'll end up at position 25 in the array. And so when you're doing something like my struct or my class dot member, it really is just saying, oh, go this many bytes past the beginning of this object, and then access the element that's there. And you're done. Does that make sense? Any questions on that? So let's talk about how variables appear. So global variables, they're stored in order of appearance. So if we have globals A, B, C, D, A will be at the lowest address, D would be at the highest address. Arguments are also stored in order of appearance. So the first argument has the lowest address. So if we had arguments X, Y, Z, X would appear, then Y would appear, then Z would appear. But they'll be next to each other in memory. And locals, they're actually stored in the reverse order of appearance. So if we had locals A, B, C, D, local D would appear before local C, which would appear before local B, which would appear before local A in terms of memory. So D would have the lowest address, and A would have the highest address. So let's talk about this, about the compiler guarding you, right? Like protection levels, public and private. There are actually no types, and there are very few protections inside the hardware itself. Most of the protections that you get for like why the compiler won't like you can't do this, the compiler won't compile it, is just from the compiler. The compiler could write that code for you, but it refuses to, right? Just like if you ask your mom for a cookie before dinner, could she give you the cookie? Yes, but she refuses to do so, right? For example, preventing access to private variables. There is nothing in the hardware that prevents you from accessing a private member variable. the compiler will just refuse to access it outside the class. But if you know in memory where things appear at, right, and where the elements are actually supposed to, and you get the address of that variable, and then you dereference it, well, hey, you can totally access that private member. I would never recommend doing it, because if you're doing this, you actually have to know how all the objects are actually laid out in memory, which probably means you have access to the source code. So, you might as well modify the source code to make it public at that point. But I'll show you an example of that next week, right? So you can get around the card. So over here we have A. He has private integers x and y. Here's public A, right? He's going to have A, use x equals 10, get x. So over here, right, we have our variable A. I type an integer pointer to be equal to A's address. So where is P pointing to in terms of A? Given what we just talked about with structs and classes. Where's P pointing at? Right, it's pointing to the beginning of A. What's at the beginning of A? X. So if I say star P equals 25, where's P pointing to? X. So what's it going to change X to? 25. So you'll print out 25 even though X is private. Because I knew where in memory it was going to be at in terms of how the object was going to be constructed. I will see you guys all in class next week. Or in office hours if you decide to stop by. Right now.